Hello friends, welcome back. Last week we modeled 3 degree of freedom equations of motion. So let us simulate that in MATLAB as well as in Simulink and finally in 3DOF block. First we have to consider an aircraft data. So let me write the aircraft data. Consider a UAV which has a mass of 13.5 kgs. IY is given as 1.135 kilogram meter square. Area is 0.55 meter square. Chord length is 0.19 meters. I am considering sea level density, that is 1.225 kilogram per meter cube. Maximum thrust I am assuming 2 kgs, and delta T will keep it as constant, that is 0.5, that is 50% of throttle is always applied. Then the aerodynamic parameters, CL naught is given as 0.28, CD naught is 0.03, Cm naught is given as minus 0.024, CL alpha is given as 3.45 per radian, CD alpha is given as 0.3 per radian, Cm alpha equals to minus 0.38 per radian, CL delta E is given as minus 0.36, Cm delta E is given as minus 0.5, and considering velocity, total velocity to be 30 meters per second. So this aircraft data, UAV data, I have considered from a beautiful book named as Small Unmanned Aircraft A by C Theory and Practice by Randall Beard and Timothy McLean. So you can refer this book for the details, and the UAV name is Aerosonde. So in the simulation, we will be needing an alpha trim and delta E trim. Now what is trim? When do we say that aircraft is in trimmed condition? The aircraft is in trimmed condition when the total forces and movements acting at the aircraft about CG is in equilibrium. Alright, that is in 0. All the forces are acting, all the forces and movements about CG are 0. So that means the pitching moment should be equals to 0. Our aim is next to find what is alpha trim and what is delta trim given the aircraft conditions. Alright. So in trim we know that we set the pitching moment equation to 0. Cm equals to Cm naught plus Cm alpha into alpha trim. I write here alpha trim plus Cm delta E into delta E trim, which is equals to 0. So many students get doubt, do we have acute dependencies over here? Obviously it is no. For trim we have rates equals to 0. Alright. So let me find delta E trim from here. We can easily write it as Cm delta E into delta E trim minus Cm naught minus Cm alpha into alpha trim, and delta E trim can write it as minus Cm naught minus Cm alpha into alpha trim divided by Cm delta E. Let us take this equation as equation number 20. Now the lift coefficient, we need lift coefficient as well. The lift coefficient to trim is CL trim equals to CL naught plus CL alpha into alpha trim plus CL delta E into delta E trim. Again, Q dependencies is 0. So we know that CL trim for a particular flight condition can be written as 2W upon rho V square into S. So we know the weight of the aircraft, we know the density, we know the aircraft is flying at what altitude, we know the velocity, we know the area. So this CL trim is actually known to us. After that, we know CL trim, and hence CL trim is known. So we can write alpha trim equals to CL trim minus CL naught minus CL delta E into delta E trim divided by CL alpha. So let me take this equation as equation number 21. Now we substitute equation 21 in equation 20 and solving we get delta E trim equals to minus Cm naught CL alpha minus Cm alpha CL trim plus Cm alpha to CL naught divided by CL alpha Cm delta E minus Cm alpha into CL delta E. So this, let me take this equation as equation number 22. Now substituting values in CL trim, since we already have the aircraft data available, substituting values in a CL trim, alpha trim, delta E trim, we get CL trim value we get, please do it by yourself. CL trim, it is 0.4368. Alpha trim, we get 0.0374 radians, which corresponds to approximately 2.1471 degrees. And delta E trim, we get it minus 0.07643 radians, minus 4.3791 degrees. So here delta E trim will remain constant throughout the simulation, and the initial angle of attack we can consider this as 2.1471 degrees. So one thing you can note from here is it is having a negative delta E trim, that is the elevator is deflected upwards. So it needs elevator deflected upwards mean there force is acting in the below direction in the tail, that means the nose will pitch up. All right. Negative elevator deflection, force is acting in the downward direction, body z direction at the tail, so that will make the nose pitch up. All right. Next, we also know that continuously alpha is changing. How you can calculate alpha? So let me draw the free body diagram here. So we have body x-axis. All right. This is where we have small u, the velocity in this direction, total velocity. All right. And here we have small w. This is the angle, attack angle. So if I drop a perpendicular from here, so this will be nothing but w. So I can write tan alpha is nothing but perpendicular upon base. So here perpendicular is w and the base is u. All right. So we can write alpha equals to tan inverse w upon u. And one more thing, we know that when alpha is not equals to 0, then obviously w will also be not equals to 0. But when alpha is 0, that means velocity is acting directly in the forward direction, body x direction, then w will be 0. So always remember that there is a 1-to-1 relation between alpha and w. That's why in many textbooks we write in place of w, we can replace it as alpha as well. All right. Now if you resolve this component of velocity, so in this direction we have v cos alpha and here we have v sin alpha. So we need some initial conditions to run our model, right? So we have initial conditions. I am denoting it as 0 in the subscript. So u naught is v cos alpha and w naught is v sin alpha. All right. And total velocity we know it is written as capital V equals to square root of u square plus small v square plus w square. So for this case we have assumed this is 0. So we have finally u square plus w square. So these relations actually we'll be using in our simulation model. All right. Now also to make things simpler, consider initial pitch angle that is theta naught equals to same as attack angle 2.1471 degrees. Since we are assuming here flight path angle, that is gamma is 0. We know that the pitch angle is given as theta equals to alpha plus gamma when beta or side slip or side velocity is 0. All right. So in this simulation we are assuming gamma to be 0, it is not climbing. So then we can assume theta naught equals to alpha naught. And the other initial conditions, we'll assume q naught, x naught and z naught equals to 0. We had written equations, right? U dot, W dot, Q dot, theta dot, X E dot, Z E dot. So we need to assume few initial conditions. So that I'm assuming, this I'm assuming to be 0. Now more or less we are ready with the all the parameters required to run in the simulation. Let us go switch to MATLAB. So let me just rerun this now. Now these are the initial conditions, that is just I have explained u naught is v into cos of angle. So this is the method to convert directly to degrees to radian. So we got alpha trim as 2.147 degrees. So this is initial condition for u naught. U naught is v 30 into cos d, initial forward velocity. It is converting it to radians. Similarly, W naught V sin alpha, sin d 2.1471 degrees, initial vertical velocity. Theta naught initial condition is again same as the attack angle. So I'm converting this to degree to radians. I'm letting MATLAB know that this is in degrees. So you need to convert it to radians. So this is initial pitch angle. And Q naught, X naught and Z naught, I've taken it as 0. And I've considered these initial conditions in a state vector, in a vector form, which is represented in this form. You can also add comma here if you want. It is completely up to you. So these are the initial conditions: u naught, W naught, theta naught, Q naught, X naught and Z naught. I have written in a vector format, and the time span I am giving it as 0 to 300 seconds, simulating it for okay, this should be 300 seconds. All right. Now we need a solver, ODE solver, with where these are the outputs t comma states. T is the time and the states are the 12 states that we have written before. And I am using ODE 45, ordinary differential equation 45. This basically uses Runge-Kutta method, which is widely used for simulating any equations of motion. And this is the function file, equations of motion, t span 0 to 300 seconds, and these are the initial conditions. You can have a look at this format syntax: help ODE 45. So this is a non-stiff differential equation, medium order method. This is MATLAB function where t span is initial condition is t naught, final time is tf, integrates the system of the differential equations y dash equals to f of t comma y from initial condition t naught to final time tf with initial conditions y naught. All right. So the syntax for this is time comma states, that is y, ODE 45, the function file that you have written, comma the time span, comma the initial conditions. There are other ODEs also available: ODE 23, ODE 78, ODE 89. I encourage you to use these as well and observe the differences. In this course, we have used ODE 45. So this is the syntax: ODE 45, added equations of motion, t span, initial conditions. And when MATLAB runs this line command 18, it searches for equations of motion. So either it searches within the MATLAB code or it searches within the folder. So I have provided it within the code. So here we have the function file, equations of motion. Remember, the name should be exact, otherwise it will not match and it will throw you an error. This is the output vector, output dy dt. I have mentioned it as dy dt. The function file is equations of motion, and the input is t comma y. You can write here t as well, no issues. But it will show that since you have not used t here, input argument might be unused. Consider replacing it with tilde. Hence, I have replaced it with tilde. And the input is, of course, the y. All right. Hope it is clear till here. Then I have added the UAV parameters: mass 13.5 kgs, moment of inertia about y-axis kilogram meter square. So these values I have already indicated earlier. I have just written here. So thrust should be in newtons, 2 into 9.81, and I have considered delta T equals to 0.5, that is 50% of throttle is always applied throughout the simulation. Alright. Next, the aerodynamic coefficient CL naught 0.28, CL alpha 3.45, CL del E, CD naught, CD alpha, CM naught, CM alpha, and so forth. Now, after coming to this, for example, line number 45, we need to unpack the states. We need to let MATLAB know that the 12 states, what are those 12 states? The first state is y of 1 is nothing but the forward velocity u. So here we have the second state belongs to w, third state belongs to theta, similarly 4 to q, fifth to x, 6 to z. Here it is saying we have not used it, so this is which is not required as well. Then we have written total velocity and attack angle. So v equals to square root of u square plus w square, alpha equals to a tan 2 w comma u. I encourage you to find out why I have used here a tan 2. I could have simply written a tan w comma u. It is related to some coordinate systems. So I encourage you to explore this term a tan 2 as well. And finally, delta E we calculated around minus 4.3791 degrees. Immediately I converted into radians, into pi by 180. And these are the aerodynamic coefficients: CL naught plus CL alpha into alpha, CL delta E into delta E, CD naught plus CD alpha into alpha, and then CM is CM naught plus CM alpha into alpha plus EM delta E into delta E. Aerodynamic forces I have mentioned before, L equals to half rho v square S into CL, D equals to half rho v square into S into CD. Then the pitching moment, half rho v square S into C into Cm. And what is T? T max into delta T, the propulsive force. Finally, we have Fx minus d cos alpha plus L sin alpha plus T, and Fg, Axc and Aze. So these are the equations of motion: u dot, w dot, theta dot, q dot, x dot, and z dot. And the final output vector is dy dt. I have written here output vector was dy dt. So I am letting MATLAB know. So these should be the outputs from this function file: u dot, w dot, theta dot, q dot, dx, x dot, and z dot. Now finally we need to run this simulation, and for plotting we need to tell MATLAB again that u belongs to the first column vector, second column is w, and so forth. Since now we are out of this function file, we need to redefine these variables. Similarly, alpha as well. Alpha equals to a tan 2 w comma u. Now finally we are ready with the simulation. So let me put a breakpoint here. Now I am running the code. Let us see if everything is working fine. And yes, you can see here in the workspace we have all the variables: alpha, u, w, theta, q, x, and z. And these are the states: 1, 2, 3, 4, 5, 6. So we are letting MATLAB know that first column belongs to u, second column belongs to w, and so forth. Hence we have written in this way. Then finally I am moving this breakpoint here. In the figure 1 I am plotting t comma u. Since I have already run it, that's why it was showing me the values of u, you can see here. And the second subplot is t comma w. In figure 2 I plotted time with theta, time with alpha. Figure 3 is been plotted with q and z. So I have written here minus z because in our equations the z axis is pointing towards downwards, that is towards the center of the earth. So we need to see whether the aircraft is increasing or losing altitude. So that's why we have written here minus. Now finally let me run this code, continue. Now let us see what we have got. So this is figure 1. In figure 1 we have U and W. So with the alpha trim and delta E trim, so U velocity remained still over there. It is constant of around 30 meters per second. W is around 1.12 meters per second. Theta is approximately 1 degrees and alpha is 2.14 degrees. Q is approximately going to 0. So we have beautiful results over here, and altitude is reducing actually in 300 seconds up to about minus 200 meters. All right. Now let us simulate same in Simulink as well using the MATLAB Simulink block. All right. So in the last lecture I have explained about this MATLAB function. So in MATLAB function everything remains same. So we have output vector u dot, w dot, theta dot, q dot, x dot and z dot, and it is up to me what other outputs I want from here. I want output alpha, I want output gamma, similarly AXE, accelerations in XE direction, similarly AZE. All right, everything remains same. So I'm not going to write this code from scratch, since I have already explained in the last week how to do this. And see here we are actually integrating these equations. I have written initial conditions y naught, and it is giving me a vector u, w, theta, q, x and z. All right. Then I am also getting output vector alpha, gamma, AXE and AZE. All right. And I have also used the two workspace that we have used it before. So it will send the data to the workspace directly in MATLAB. Further, I have also plotted these curves, that is the vector u dot, w dot directly before integration. All right. And to run this Simulink model, I have written another MATLAB code. This is the one. So everything remains same over here, except I am calling Simulink simulate 3DOF simu dot slx. So this is the file name, 3DOF simu. All right. So let me see if it is running well or if there is any error. I am putting a breakpoint over here and click on run. So it seems it is working fine. So let us continue plotting. So I have extracted theta, q, alpha and gamma from that two workspace model, and I am plotting it here. The format remains same. I am clicking on continue. So we have pitch angle, angular velocity, and similarly we have angular. All right. We have theta, pitch angle, this is q, angular velocity, this is alpha, this is attack angle in degrees, or you can directly convert it to degrees. Currently it is showing in alpha, or let me check it. Yeah, so it is already converted into degrees, so that's fine. This is attack angle, flight path angle. All right. So here we have theta, pitch angle, q, angular velocity, attack angle degrees, gamma, flight path angle, which is in degrees, not degrees per second. Right. So let me rerun it. Now it's okay. So we get similar results as per the previous MATLAB code. Now we can also check it here as well in the code. If you see here, this is the U scope that we are getting over here. So it is a trim value of approximately 30 meters per second. Let me close it. Similarly, W, theta is approximately 1 degrees. Q should go to 0 for trim value. Yes, it is going to 0. So here we have pitch angle theta. You can confirm it from here. Yes. All right. Now next let us check gamma. We have entered gamma here, right? So theta is total angle of attack angle plus gamma. So let us see what is gamma over here. Approximately -1 degrees. And what is alpha over here? It is coming to around 2.145 degrees. So total angle would be around 1 degrees. All right. Now we are done with this block of MATLAB function. Now initially we thought of using this block directly, 3DOF block that I've shown you earlier. Let me open it again. So this is the 3DOF block. So instead of writing a separate MATLAB code or using the MATLAB function block, you can use it directly. So if you notice it carefully, we need 3 inputs, that is forces in x direction, forces in z direction, and then the moments, that is newtons per meter. And the output is theta, q, acceleration dq by dt, xe, ze, u, w, that is small u and small w, acceleration in body axis, axb, azb, similarly axc towards the with respect to inertial reference frame. All right. Now I can directly run this code and see. Let me close these figures first. All right. Now let me run this code directly. Now before running, let me show you what do I have here. I need to give this an input vector forces in x and z direction. So I have written output here as fx and fz. Movement about y axis, it is up to me, and similarly cm, and inputs it only needs now u and w. So need not to write the complete code over here. So we need only fx and fz so that we can give that information directly to the block. Now the equation that we had written here after this, so these are already embedded into the block. So need not to write those equations here, that which is unnecessary. So we need fx and fz, and we also need movements about y axis. Hence I have written the output vector here as fx, fz and my. The number of outputs that you write over here, it will directly appear over here, fx, fz, my, alpha and cm. So this signal is going to fx, fz is going to fz, and my is going to the moments m. All right. I hope it is clear. And I've converted directly to radians to degrees and all these to the desired units as we want. All right. Now we are ready to run this code. Yes. So it is showing over here ready. So let me show here what is theta over here. So theta is coming around 1 degrees. Let me go to the previous block. The theta was approximately 1 degrees. So we got the same. Similarly, alpha is the trim values around 2.145 degrees. So let me go to the block. So here we have approximately 2.14 degrees here as well. So you can compare this. So this in this block the equations are already inbuilt. So you need not to write the equations and integrate separately. All right. So you can use this block directly if you have the aircraft model. Similarly, you can compare the other parameters as well. For example, AXB, which is approximately 0, accelerations. You go to the previous block. So here we have accelerations, it is going approximately equals to 0. This is nothing but u dot. All right. The first vector for this dy by dt is u dot. This is before integration. After integration obviously will be u. Similarly, this is w dot. All right. It's approximately going to 0. So in this way you can actually compare all the plots, whether are you getting the similar plots or not. So these are the different methodologies that you can use to simulate 3 degree of freedom equations of motion. I hope now you know how to simulate the 3 degree of freedom equations of motion. In the next lecture, we'll begin with the simulation of 6 degree of freedom equations of motion. Thank you.